Assalamu alaikum viewers. The topic of today's video is the characteristic of state functions. So today's video is all about the discussion of the characteristic of state function. So state function's value is determined by the state of the system and it does not depend on the path by which the state is reached. You already know this, that state function depends only on the initial and the final state of the system. It does not depend on the path through which the change has been brought. Let's just say that I have a balloon and I inflate air. I blow air into that balloon. Well, the pressure in the balloon will only depend on its initial and the final value. Okay, the pressure in the balloon will only depend on its initial and the final value. It will not depend on whether the pressure has been changed with the help of a blower or with the help of your mouth. It does not depend on that. Well, the second thing that we have is that the state function depends only on the initial and the final state. That is, delta v is equal to v2, v final state minus v1, the initial state of the volume. So volume is another example of the state function. You know, the other example of the state functions are like volume, temperature, enthalpy. So these are all just the examples of the state function. Okay, so the third point is the differentials of the state functions are exact. As you know that state functions are those that depends on the initial and the final state, and their differentials should be exact. Whereas when I talk about the path functions are those quantities whose value depends upon the path followed. So the differentials of the path functions are not exact. The differentials of path functions are inexact. Okay, so what does it mean? It means that energy, let's just say that energy is a state function. You already know that energy is a state function, and the value of energy is independent of the path followed. So here, dE means E2 minus E1. Okay, and delta E is equal to integration 2 is the final state and 1 is the initial state, and dE the change in the value of energy. So I can say the dE here is E2 minus E1. E2 is the final state and E1 is the initial state. And when I take the integration, and that's equal to del E. So I can say that the value of energy depends only on the initial and the final state, and it does not depend on the path followed. Whereas when I talk about the path function, we cannot say dW is equal to W2 minus W1. Why can't we say dW is equal to W2 minus W1? Because the work depends on the path followed. So why cannot we write dW is equal to W2 minus W1? Because work does not depend on its final and the initial state. It certainly depends upon the path followed. It certainly depends on how the final state is achieved. Okay, so in the case of the work, we need to determine each steps through which has work reached its final state. So that's one of the example of the path function. So I can say that the differentials of the state function are exact, whereas the differentials of the path functions are inexact. Okay, so moving on towards this pressure volume diagram, as you can see here that along the y-axis is pressure and along the x-axis is volume, and this is a cyclic process. And as you can see here that the system is at the initial state, pressure P1, volume V1. After some time, the pressure is decreasing and the volume is increasing, and the system reaches another point at which the pressure has decreased to P2 and volume has increased to V2. And the system then compresses again, and then the volume decreases and pressure increases, and the system reaches again to its initial value. So in this cyclic process, as you can see that there is no change in pressure between the initial and the final state. As you can see here that the system starts from here and then ends again at this point. So there is no change in pressure and no change in volume. So change in pressure and change in volume will be zero. So I can say that the state function, for state function, the change in pressure and change in volume of a cyclic process is zero. Whereas if I talk about state function, let's just take an example of work. As you know that work is a state function. So in that case, when the system changes from its initial value to another value and then goes back again to its initial value, then this is a cyclic process, and in that case work done will be equal to the area that is covered by this curve. Okay, the area that is covered by this figure. Okay, so let's just say another example here, that for example if my pressure changes from this value to this value means the pressure has decreased a lot and the volume has increased a lot, and then the system goes again to its initial value. Then as you can see here that the figure will cover more area, and in that case the work will be more as compared to this figure. This means that the work depends upon the path followed, whereas the pressure and volume does not depend upon the path followed. So in a cyclic process, when I take the change in state function, then that would be equal to 0, and whereas in a cyclic process, when I talk about some path function, then the path function will have some value, and that value will be equal to, for example, let's just talk about work, then the value of that work will be equal to the area that is enclosed by the curve. So the fourth and the final property of the state function is that if the function is a state function, its value will be determined by two or more other variables. So I can say that the value of the state function is correlated to two other state variables. So let's just say that E is a state variable, and then its value will be depending upon X and Y. Okay, for example, that PV is equal to nRT. You already know about PV is equal to nRT. When we take N to be constant and R is already a constant, then pressure, volume, and temperature are correlated. The pressure is the function of volume and temperature, and similarly volume is the function of pressure and temperature is the function of pressure and volume. So so I can say that each of the state function depends on two or more than two variables. So what do I have here is that energy E is a function of X and Y. So that will be equal to partial differential of A divided by partial differential of X y d of x plus partial differential of A divided by partial differential of y x dy. So that's just an equation that is representing us that the state function depends upon the two other variables. So here, as you can see, this sign here is the partial differential. Okay, this sign here is the partial differential, and that's showing us that energy is dependent upon x. The change in the energy is dependent upon the change in the value of x. And similarly, this here again is a partial differential, and this again here is a partial differential of y. And that shows us that the change in the value of energy also depends upon the change in the value of y. So I can say that energy is a function of some variable x and some variable y. Okay, so that are the characteristic of the state functions. So that was all for today's lecture.